We said Charles Keeling was an excellent student and did exactly what his advisor suggested and started measuring CO2 in the atmosphere on Mauna Loa away from all civilizations. Hawaii has become much more touristic and so on, but this station on Mauna Loa, high on the mountains, 3,400 meters up, still measures CO2, and we have a nice long time series which tells us CO2 is not only increasing but it is increasing faster and faster, which means what? We are trapping more and more of the thermal energy. The greenhouse effect is getting stronger and stronger. The blanket is getting thicker and thicker, which means we must be getting warmer. But are we also getting warmer faster and faster because CO2 is increasing faster and faster? We need a long enough time series to see this as well, so we'll see how it is done. So here is a nice tree ring that is being shown. So you take a core of a tree's trunk that lives long enough, and a very nice story about why some trees can live such a long time. Every species has a lifespan. Human beings used to live just for 30-40 years before. Now we live for 70-80 years. Lifespan has increased, health care has become better, our diets have become better, and so on. But trees, some of them can live for hundreds if not thousands of years. Okay, they don't age so fast, but when they grow they produce rings like this. So this is the center of the tree trunk and it's going out like this. Why does it happen this way? Because each year as the tree trunk grows, it grows based on how much rain happened, how warm or cold it was. So you can see the tree rings are closer to each other, sometimes they are farther from each other sometime, and so on and so forth. So on the internet, now we are starting off the discussion of the growing hockey stick. On the internet you can quickly look up how hot it was on the day you were born or on any other day in the past, because now everybody is tracking the data. Scientists began measuring and recording the temperature way back in 1706, but there are no figures from before 1706. So how do we know how hot it was before that? There are all kinds of sources for that information. They are not as reliable as a thermometer which directly measures temperatures, but they are not far off. We can use them carefully, and if you're old enough you know what it means when I say you have to calibrate them and validate them and make sure it is precise, which means you can measure many times and get the same answer, and it's very accurate, which means you can compare to a standard and it is within plus minus 0.1 degree or whatever the accuracy is. So you can look at tree rings, for example. Here the number of rings will tell you what the age of a tree is. So you count from inside to out. Each year it's putting a band, so you know how old it is. Okay, this works not only with trees that have just been cut down, but also with fossil trees that have been in the ground for thousands of years, because they were born at some point, they died at some point for whatever reason, but they are preserved, which means this date and information is preserved as well. You can tell from tree rings whether a year was hot or cold, wet or dry. During a hot, wet summer, a tree grows faster, and so the rings are thicker than in cold summers. So it doesn't grow much here, but it grows a lot here when it's got nice conditions of warm and wet summer. Researchers also drill into the ground, into the seabed, and into the ice caps, which are those glaciers on land that we discussed before. This makes it possible for them to bring the details up from long time ago. The deeper you go, the older the material. It is just like the laundry basket or a stack of comics. The oldest underpants and the oldest comics are at the bottom because new ones keep getting piled on top. Are you piling up your comics in a corner somewhere and not properly arranging them, and mom is always telling you to clean your room? Well, if you pile them up, you know how this works. At the end of the 20th century, the American scientist Michael E. Mann and two of his colleagues made a graph that's become very famous. It shows the temperature over the past 1,000 years. In order to gauge the temperature, they researched thousands of tree rings. The graph became so famous that it had a nickname, the hockey stick. And as I mentioned in the last podcast, here is the hockey stick. So you are going back from about 1,000 years. You're coming forward, coming forward, coming forward. You hit industrial revolution and boom, the temperatures start shooting up. Okay, the stick is lying with its long side on the ground. That long side is the temperature in the years 1000 to 1900. So now we call it Common Era 1000 to 1900, which was already the well into the Industrial Revolution. It runs more or less in a straight line, which means the temperatures were not doing much. They were fairly flat, and then it went up suddenly, with temperatures remaining about the same for 900 years here. But from 1900 on, it goes up steeply. This is the blade of the hockey stick, the short part here. For the last century, the temperature on Earth has risen quickly and it has kept on going. The hockey stick is growing here, which means what? CO2 is growing as well, and the other greenhouse gases also. This is the change in temperature. When is it a change in total temperature? If you put a thermometer, you say your body temperature is 98.6 degree Fahrenheit or 37 point something, but this is how warm it is compared to some long-term average and how cold it is compared to some long-term average. If you don't know, don't worry about it. For those who are older, you know what climatology means and what anomaly means. So if even if you're young today, if you say, oh my god, I'm feeling very hot, then this day of, let's say, June 15th, you expect the temperature at your place to be at a certain level, but if it's much warmer than that, you are saying it's too hot. So you have just said the anomaly is warm. Okay, so you are a climatologist. So here is the measured temperature with thermometers here, which only came from 1706 onward. Before that, temperature from other sources such as tree rings are estimated, and you can see that maybe it was even cooling a little bit because we had the famous little ice age. Remember, there was a slight cooling, and before that we were warm during the medieval warming when the Vikings went to Greenland and so on. And here is Michael Mann, was born in 1965 and is doing very well now at the Pennsylvania State University in the US. Okay, so this goes from year 1000 to year 2015 or so. Okay, the creators of the graph received a lot of criticism. People thought they had not measured the changes properly. You couldn't even see that couldn't even see that it was a bit warmer 1,000 years ago when we know it was warmer, and a bit cooler 500 years ago. So 20 years later, they did their research again. Many more techniques of measuring even more precisely had come in 20 years along in the meantime. But the results were the same. The Earth was warming up at a fast pace since about 1900. Other scientists used different methods and came to the same conclusion. Yes, it's all true. Michael Mann and his team were correct that the hockey stick is right. And what it says is that when you go in the past and use tree rings to estimate warmer than normal and colder than normal temperatures, it is not very precise, that it will be a little bit uncertain, but that doesn't change the results. When it is this cold or this warm, it is very correct. So in the increase that you see in CO2 can also be seen in the temperature. So the physics is working. We know that if you increase greenhouse gases, we trap more thermal energy and the Earth should be warming, and the temperature measurements say yes indeed, the Earth is warming. Right? Arrhenius was right as well. The more CO2 there is, the hotter it gets, but Keeling only went back to 1958 and the hockey stick only went back to the year 1000. However, we know that the climate can change a lot in the long term. We already talked about ice ages and so on. So what were the temperatures and the amount of CO2 like long time ago? You have to go into the cold to find that out. So you know that we're going to go and talk about trapped in ice. There are many signatures of past climates trapped in ice as well, which we will come back and discuss in the next podcast. Okay, so I will come back and do that, and you get some rest and tell me if you're enjoying this. Tell your parents, friends, teachers whether you are learning anything from grandpa, Ajja. Okay, see you.